Hi everyone, welcome back with another video in a series of first order differential equation. So today we will be learning about Bernoulli equation, whereas Bernoulli equation takes in the general form of dy over dx plus px times y equals qx times y to the power of n. But wait a minute, if I remove the y to the power of n here, you will notice that this differential equation is indeed a first order linear differential equation. But for Bernoulli equation, there will be a y to the power of n that makes this differential equation becomes a nonlinear one. And how to solve for Bernoulli equation? You will need a u substitution process, whereas it is likely similar with the substitution homogeneous differential equation that we did in the previous video, but this Bernoulli equation will take a simpler or not as complicated as a substitution homogeneous algebraic manipulation, and where after you did the substitution process, it will give you a first order linear differential equation that you can solve for. Well, you all might be confused about what am I talking about right now, but after I showed you guys the first example, I believe that you all will feel confident about solving for Bernoulli equation. So without further ado, let's go to the first example. Hi everyone, so this is our first example for today's Bernoulli equation. We have here x times y xn or dy over dx plus y equals to 1 over y squared. And our very first step is I want to rewrite this Bernoulli equation in a simpler way so you all will notice what's going on here, and I will bring up the 1 over y squared to the top, and that will give y to the negative 2. And first, you will see here that there is an x in front of y-axis, which you will always want to have a constant of 1 in front of y-axis. And that is why I'm going to multiply this whole equation by x to the negative 1, or actually 1 over x is fine, but multiplying everything by x to the negative 1 will give us y-axis plus x to the negative 1 times y equals to x to the negative 1 times y to the negative 2. And after we multiply everything by x to the negative 1, we will see that this is in the general form of a Bernoulli equation. And we're ready to solve it. So what's the first step? The first step is that let's calculate for our substitutions here, which we know our n is negative 2 here. Remember? Okay, so our n is negative 2. And so we can calculate for our u here. U is equals to y to the power of 1 minus n. Our n, since our n is negative 2, 1 minus negative 2 is just 1 plus 2, which y is to the power of third. And so let's calculate for our y-axis substitution as well. So we know that 1 y-axis is equals to 1 over 1 minus n times y-axis, or y to the power of n, times u-axis. And this will equals to 1 over 1 minus negative 2 is just 3, 1 plus 2, times y to the power of n, and which we know that n is negative 2, times u-axis. U-axis is just u-axis. After we've calculated our substitution here, let's plug them in into our differential equation right here. Okay? So we know our y-axis is equals to this thing here, which is 1 over 3 y to the negative 2 u-axis plus x to the negative 1 y equals to x to the negative 1 times y to the power of negative 2. And since we want to make this into the form of a first order linear differential equation, we cannot have this variable in front of u-axis because we want a constant of 1. Remember, okay? We always want a constant of 1 in front of a y-axis or u-axis or x-axis or anything. So let's multiply everything by 3 y squared. And so after multiplying all of the equation by 3 times y to the power of 2, we will get uxn plus 3y to the power of 2 x to the power of negative 1 times y, or actually this will give us 3y to the third power times x to the negative 1 equals to y to the negative 2 times y squared is just y to the 0, which is 1. So on the right side, we will get 3x to the negative 1. And what we can see here that we can substitute our u here, which is y to the power of third, with our y to the power of third that we've got here after we've multiplied everything with 3y squared. And so we're going to substitute that with u, which is 3x to the negative 1, u equals to 3x to the negative 1. And so at this point of step, I know you all may think that this is already in the form of first order linear differential equation. And you are all correct because we can solve this for a first order linear differential equation. And so using the same steps like for our first order linear differential equation, we're going to identify the variables first, which is px is equal to 3x to the negative 1. Our qx is 3x to the negative 1 as well. And let's find for our integrating factor. Remember, we need an integrating factor in our first order linear DE, which is e to the power of the integration of px dx. And so e to the integration of 3 over x dx. This is just e to the third ln of x. And so we can do it in this way, e to the ln x to the third, and we can cross out the e and ln, and this will end up as x to the third. And so remember, for our first order linear differential equation, we will multiply our integrating factor with our new differential equation or new linear differential equation that we've gotten here. Okay, so let's multiply everything here with our integrating factor, which is x to the third power. And so after multiplying everything, we will get x to the third uxn plus 3x squared u equals to 3x squared. And remember, at this point of step, let's check if we did our first order linear differential equation correctly. Okay, let's check. Our x to the third power here, if we take the derivative of it, it will equals to this thing here. As well as, if we integrate our 3x squared here, we will get an x cubed here. And so, it proves that our steps for finding the integrating factor is correct. And so we can continue, which is d over dx, or the derivative of x, the integrating factor times u, because later we want to make this into a y equals equation, and you know u is a substitution for y to the third power here, and so it will equals to 3x squared. And if we want to remove our derivative here, let's integrate both sides, which gives us x cubed u equals to the integration of 3x squared dx. And after we integrate our right side there, 3x squared is just x to the third power, or x cubed, plus c. Don't forget the constant, okay? And so after we get this x cubed u equals x cubed plus c, let's multiply everything by 1 over x cubed, since we want to make this final answer as an explicit answer. And so u is equals to 1 plus c over x cubed. And we know that u here, we can substitute it back with y to the third power, since we want to make this equation into a y equals equation, not u, okay? So let's plug our y cubed here for the u equals to 1 plus c over x cubed, and we can solve for y. And y, to remove the cube on the left hand side, we must cube root both sides. So y is equals to 1, 1 plus cx to the negative third bracket 1 over 3, or the cube root of 1 plus cx to the negative third. And so this will be our final solution to this Bernoulli equation. And remember, our first step is that we want to calculate our substitution here. And after we've calculated our substitution, plug in the y-axis and also multiply everything by what's in front of the y-axis to be gone, and you will get a first order linear differential equation to solve right here. And after that process, you're good to go. You can solve for first order linear differential equation easily at this stage. So let's move on to our second example. And so this is our example 2 for today's Bernoulli equation. We've got here dy over dx, or y-axis, equals to y times x y to the fourth minus 1. And so I would like to rewrite this Bernoulli equation, or this differential equation, into y-axis equals to, I would like to distribute this y inside the parentheses by multiplying everything by y. So this will give us y-axis equals to x times y to the fifth minus y. And I would like to make this differential equation into the general form of a Bernoulli equation by subtracting y into both sides, or actually adding y into both sides. And this will give us y-axis plus y equals to x times y to the fifth. And from here on, you'll notice that this is already in the general form of a Bernoulli equation, which our next step, you would already know that we're going to calculate for our substitutions here, which is u, which are u and y-axis. And so we know our n here is equals to 5, which is this thing here. And we can calculate for u, which u is equals to y to the 1 minus n. And y to the 1 minus n is that 1, y to the 1 minus 5 is just negative 4. And so we can also calculate for our y-axis here, which is our y-axis is equals to 1 over 1 minus n times y to the n power multiplied by u-axis, and our y-axis will equals to 1 over 1 minus n here, 1 minus 5 is negative 4, so it's negative 1 over 4 basically, times y to the n is y to the fifth times u-axis, because u-axis is just u-axis. Now let's substitute our y-axis here into our y-axis over here, okay, like the previous example. So it's negative 1 over 4 times y to the power of fifth times u-axis plus y equals to x times y to the fifth power. And remember, we want in front of our u-axis here to be a constant multiplication of 1. So let's multiply all of the whole of our differential equation here by negative 4 y to the negative fifth. And so this will give us, this will remove the whole thing here, and this will just be u-axis plus y multiplied by y to the negative fifth is just y to the negative 4. So this will give us negative 4 times y to the negative 4 equals to x y to the fifth multiplied by negative 4 y to the fifth, or to the negative fifth will gives us negative 4x. And from here on, let's substitute our y to the negative 4 here with u here, because u is equals to negative y to the negative 4. And so, this will give us ux minus 4u equals to negative 4x. And from this step on, I know you all may think that this is in the form of linear, first order linear differential equation, and you are all correct, and we can solve for it. Okay? So, let's solve this by determining our variables first, which px is equals to negative 4, our qx is equals to negative 4x, and our integrating factor that we want to find is equals to e to the power of integration of px dx, and our integration or our integrating factor will equals to e to the power of the integration of negative 4 dx. This will equals to e to the negative 4x, and this will be our integrating factor. Now let's multiply our whole differential equation that we've gotten here with our integrating factor, which is e to the negative 4x, and this will give us e to the negative 4x times ux minus 4e to the negative 4x times u equals to negative 4x e to the negative 4x. And now let's check whether we've done our steps to find the integrating factor correctly or not. Okay, so we can see that if we take the derivative of e to the negative 4x here, it will equals to negative 4e to the negative 4x here. And likewise, if we integrate this negative 4e to the negative 4x, we will get e to the negative 4x. That means we have done all of our steps correctly in order to find our integrating factor, and we're good to go in order to solve for this first order linear differential equation, which dx or d over dx is the integrating factor of e to the negative 4x times u, because we want to make this into y equals equation, equals to negative 4x e to the negative 4x. And to remove the derivation on the left hand side, let's integrate both sides. Okay, that will remove the derivative, and this will equals to e to the negative 4x times u equals to the integration of negative 4x times e to the negative 4x dx. And remember, at this step, we can do the integration by parts through the Tanzania method, which is an easier way rather than you're using the formula u phi minus the integration of phi du. Okay, remember, we're going to integrate this one using the integration by parts of Tanzania method, which is this is the derivative and this is the integration. Okay, and so negative 4x, let's take the derivative of it, it will becomes negative 4, and negative 4 will become 0, and e to the negative 4x, let's take the integration of it, it will becomes negative 1 over 4 e to the negative 4x, and one more will gives us 1 over 16 e to the negative 4x. And then let's multiply this one with the positive sign, multiply this one and this one, negative 4 and 1 over 16 e to the negative 4x with a negative sign. And this integration, or integration by parts, will gives us e to the negative 4x times u equals to x, or 1 negative 4x times negative 1 over 4 is just equals to x. That means x e to the negative 4x. The negative sign get rid of each other. And also, this one here, negative 4 times 1 over 16 e to the negative 4x will also be positive. And 4 times 1 over 16 is just 1 over 4 times e to the negative 4x. And don't forget here, plus c, or add a constant. And after this one, let's multiply the whole equation with e to the 4x, because we want to get the e to the negative 4x on the left hand side to be gone, which this equation will become u equals to x times e to the negative 4x times e to the 4x. It will cross out the e's, which only gives us the x, plus 1 over 4. This also cross out the e's, which gives 1 over 4, plus c e to the 4x. Now, our last step is to substitute our u back with y to the negative 4 here. And so, u is equals to y negative 4 equals to x plus 1 over 4 plus c e to the 4x. And then we can write this as 1 over y to the power of 4 equals to x plus 1 over 4 plus c e to the 4x. And we can multiply both sides by y over 4 over x plus 1 over 4 plus c e to the 4x, and also the other side by the same variables, which is y to the power of 4 over x plus 1 over 4 plus c e to the 4x. And so this will cross out the y to the power of 4, and this will cross out the whole thing here and the whole things here, and this will gives us y to the 4th equals to 1 over x plus 1 over 4 plus c e to the 4x. And to get rid of the power of 4 here, we have to multiply everything to the power of 1 over 4. And so our final answer here will be y equals bracket 1 over x plus 1 over 4 plus c e to 4x, bracket again, to the power everything to the power of 1 over 4. And this is our general solution to this Bernoulli differential equation for example number 2.